Hi, everyone. So I'm going to go through the sum and difference identities for the sine, cosine, and that should also say tangent functions. So apologize for that. But these are two identities at the top of the worksheet for sine and cosine for the sum or difference of two angle values. So I started off by listing what the identities are. So the sine of some angle, we'll call it A, plus or minus some angle B, is equal to the sine of that first angle multiplied by the cosine of that first angle. Let me pause this for a second and back up. Plus minus the cosine of that first angle times the sine of that second angle. And what I've done here is color code that so it's kind of clear, I hope. All right, so once we look at an example, I think this will make a lot more sense, but pay attention to the color coding as we move forward and pay attention to the plus and minus signs separating the two terms. All right. The identity for cosine, very similar in structure in some regards, yet very different in some regards. So the cosine of the sum or difference of two angles is equal to the cosine of A times cosine of B minus plus the sine A times sine B. Again, this sounds like gibberish. Don't be discouraged if it does. Right now, I just want to lay these out. Pay particular attention to the cosine identity. The signs are reversed. Pay attention to that. So we're going to look at an example right now. How would we find the exact value of 195 degrees? So you start by determining how can we make 195 as the sum or difference of two common values. And this takes a little bit of guesswork, but we quickly can find out that 135 plus 60 degrees makes 195. And the reason I chose those values are because they're angles of rotation along the unit circle. So we begin by rewriting 195 as the sum of two angles. And now we're going to apply the identity, the sine for the sum of two angles. And I'll pause right here for a second. So pay attention to the color. Looking at the sine of A plus B, we take the sine of A, in this case 135, and we also take the cosine of B. We're going to multiply those values together momentarily. Then we take the cosine of 135 and multiply it by the sine of 60. And again, we're about to evaluate those and do the products. So the rest now are just values found along the unit circle. I might speed this up just a tiny bit here, skip this 5 seconds. Okay. And I'll let you confirm that those values are correct. All I'm doing now is arithmetic. I'm multiplying and I'm adding to get a final answer of the square root of 2 minus the square root of 6 divided by 4. Okay. There are other worked out examples in the book. I'm going to do another example using the cosine, and I also chose to do an example that includes a negative angle of rotation. So to make, when dealing with radians, what's typically a little bit easier is to look at the denominator. In this case, it was 12, and take your common angles of rotation in radians, which are pi over 6, pi over 3, and pi over 4, and write those in with a denominator of 12 equivalently. Okay, and that makes it, I think, a bit easier on how to write your angle of rotation. So in this case, after rewriting the common angles of rotation with denominators of 12, I quickly noticed, hey, if I take 4 pi over 12 and 3 pi over 12 and combine them, that makes 7 pi over 12. So therefore, negative 4 pi over 12 and negative 3 pi over 12 would make negative 7 pi over 12. And there we go. So I found how to write negative 7 pi over 12 using common angles. And I will pause this right here. So pay attention to this part right here. So cosine of A, cosine of B, in this case, I believe it was negative 4 pi. And this will be 3 pi over 12. I'm sorry, negative 4 pi over 12 and 3 pi over 12 because I have them separated by minus. So really pay attention to the structure. And then I'm about to write a plus sign in between since there's my two angles are separated by minus of the sine of negative 4 pi over 12 multiplied by the sine of 3 pi over 12. I believe I have that right. Let's just see. Right. But pay careful attention there and rerun this video as you need. So there's my A. My B, pay attention, right? So since my two angles are separated by subtraction, I'm just writing 3 pi over 12 here. Again, re-emphasizing the point that since my two angles are separated by subtraction, in the cosine identity, I need to separate those two terms with a plus sign. And at this point, that is the application of applying the identity. The rest is just using the unit circle to evaluate these values. So I'll skip ahead a tiny bit or just go a little bit quicker, excuse me. So I'm evaluating, I'm doing arithmetic, I'm combining the fractions and circling my answer. Right. This is an example of kind of using the identities, maybe if you want to think of it as reading from right to left, but remember equality is the same forwards as it is backwards. 2 equals 1 plus 1, therefore 1 plus 1 equals 2. So what I'm doing here is looking at, well, I see I have a 5 and a 6 as an angle of rotation. So in my mind, I'm kind of thinking I have 5 and 6. Those are my A and B. And the structure of this is cosine, cosine, minus sine, sine. And just comparing those to the identities, let me just back this up for 1 second. Okay. Let's stay there for a moment. Comparing those back to the identities, this fits the structure of the cosine of A plus B, right? So compare those to the two identities at the top of the sheet, and you'll notice this fits nicely. If we let 5 be A and 6 become B, this exactly models the identity. So kind of just using the identities, again, if you want to think of it in reverse or reading it from right to left. We're going to use not just the sum and difference identities in this example, but we need to also use our even odd identities. So from section 3.1, when we have the sign of an angle, a negative angle of rotation, that's equivalent to the negative sine of that angle of rotation. So I'll just keep it simple and say, refer back to section 3.1, the even odd identities. At this point, you should have practiced it in MathLab prior to doing this lesson. And after applying the even and odd identities, I also notice I'm going to factor out a -1. And this helps me see the structure of sine pi over 2, cosine pi over 5, cosine pi over 2, sine pi over 5. Very wordy, but pi over 2, if you consider that the A and pi over 5 is B, the structure of that expression models nicely as the sine of pi over 2 plus pi over 5. And I'm just going to do some arithmetic and add pi over 2 to pi over 5 and get a final answer of 7 pi over 10. And that -1 that we factored out before carries along all the way through. So this is your first sheet. Please feel free to go back and watch whatever example you need to again. Also send me an email. I do ask you at this point to copy the CoFunction identities listed in your book or online in the e-text, page 188. So that's why I purposely left that spot blank for you to copy down. You can do the reading in the book to have a little more information about it, but I just want to use this time to do some examples. So I will pause. These are pretty easy identities in the sense that from geometry class in high school, you might have been taught that supplementary angles add up to 180. Complementary angles add up to 90, right? So that's, if you have any children or if you remember from high school geometry yourself, that's the definition of supplementary and complementary angles. Well, it's no coincidence, and it's not by accident, that we name sine and cosine in that manner. Cosine really is an abbreviated form as the complement of sine. So I'm not going to get bogged down here, but I'm taking the time to stress this because it might be a little bit helpful when you need to memorize these identity. So a CoFunction identity, think complementary, think add to 90. So the sine of, I'll keep it simple, 50 is equal to the cosine of 90 minus 50, or the complement of 50, which is 40. So saying that nice and smoothly, the sine of 50 is equivalent to the cosine of 40. Similarly, the tangent of 89 degrees is equivalent to the cotangent of 1 degree. Right? So cofunctions really, and it's not just a trick, it is how the names were derived. You consider complementary angles, and remembering from high school or just looking it up, complementary angles sum to 90 degrees. So that helps with the CoFunction identities. So therefore, these questions are relatively easy. Find the exact value of the sine of 15 degrees using a CoFunction. So first we can rewrite the sine of 15 degrees as the cosine of 90 minus 15, or 75, since 15 and 75 are complementary. And now to find the cosine of 75, think about what we just did on the previous slide, okay, where we need to find a way to write 75 as the sum or difference of two common angles. And what I've just showed there is that you can do it using 45 degrees and 30 degrees, right? So I went back there, looked at the identities, trying to use the same colors for you to remember how to write this. And at this point, I'm just evaluating, I'm just applying the identities. And then the next two steps, I'm going to evaluate using the unit circle and then just use arithmetic to work the numbers. So I'm just going to skip through 5 seconds at a time here, kind of speed it up. And that's it. So that's a question that took a little more work, but very reasonable. Okay, so if you're asked to use a CoFunction, complementary angles, the complement of 15 is 75. So the sine of 15 is equivalent to the cosine of 75. And then from there, we use the strategy from the front side of that worksheet to make 75 the sum or difference. I chose sum of two common angles, blah, blah, blah. There we go. Onwards to the tangent. The derivation of the tangent, also laid out in the book, comes from the definition that tangent is the sine over, or the sine of A divided by the cosine of A. But don't worry about the derivations. Here are the formulas for you. So the sum or difference of two angles that involve the tangent function, right there. Tan of A plus or minus tan of B. Those two terms collectively divided by 1 minus plus, so we got a little reversal in sign there, tan A, tan B. So let's find the exact value of the tangent of 75. So from the example right above, I've already shown how we made 75 using two common angles as 45 plus 35. And now just pay attention to the structure. And I believe the color should help here. A is equal to 45 degrees. B is equal to 30 degrees. We're using the sum. We're adding those. So we're following the structure of the identity. This step is just straight up substitution into the identity. You probably know what follows next. Now we're going to look at the unit circle. At some point that should be committed to your memory, or at least be able to derive it for future coursework. But tangent of 45 evaluates to 1. The tangent of 30 is the square root of 3 divided by 3. So making those substitutions. Now I'm just going to full screen this. So I'm doing a tiny bit of algebra that I do want to slow down with. So I kind of have an ugly looking stacked fraction here. All right, so pay attention to that. So what I'm doing is I noticed there's a denominator of 3 in both the numerator and the denominator. So I'm going to multiply by 3 to clear that out. If you want extra review with this, you can Google search complex fractions, particularly simplifying complex fractions. But this is about the extent you'll need to be able to do in homework questions. Okay, so just notice in both the numerator and the denominator, you have a denominator of 3. So multiplying the numerator by 3 and distributing as will clear that fraction. But to keep it mathematically legal, we have to multiply the denominator by 3. And we'll use distribution, and that's helpful because it's going to eradicate the denominators. So distributing the 3 into the numerator, we have 3 plus the square root of 3. In the denominator, we have 3 minus the square root of 3. Now, once again, some more algebra, not trigonometry here. This is called rationalizing the denominator, a skill we practiced again earlier this semester, coming back up now, with 2 terms. To remind you how to do that, you focus solely on the denominator, which is 3 minus the square root of 3, and you multiply by what is called its conjugate, 3 plus the square root of 3. You just change the signs in between the terms, okay? You're going to FOIL, expand, distribute, whatever verb you use here, but you're going to expand out those 2 binomials, both in the numerator and denominator. But there are some shortcuts. So when I look at the denominator, I do notice that it is a difference of squares. If you don't know what I'm talking about, then just use your method of foiling or expanding. But for those of you who are familiar with the difference of squares, the denominator becomes 3 squared minus the square root of 3 squared, known as 9 minus 3. And the numerator expands out as written. The rest here is basic arithmetic, combining like terms, simplifying, and complete. These were the examples I was thinking of earlier when I said these are really simple, quick questions. Write each expression as an equivalent cofunction. The complement of 20 is 70. So sine of, I lost what that was. So the sine of 20 degrees is equal to the cosine of 70. 85 degrees has a complement of 5 degrees. So the cotangent of 85 is equivalent to the tangent of 5 degrees, keeping it simple. Lastly, the cosine of pi over 12. Well, now we're given radians. Just remember that 90 degrees is pi over 2 radians. So to find a complement, you subtract. Pi over 2 minus pi over 12. Doing a little bit of fraction work there, finding a common denominator. This becomes 10 pi over 24, which simplifies to 5 pi over 12, the sine of 5 pi over 12. Pretty straightforward. The last example, you're definitely going to watch this maybe twice, okay? It's not ridiculously hard. It's just a few steps. I've done my best to color code this. There's another example in the book that you can read. You can probably find a multitude of videos, additional videos on YouTube for extra practice. So this is kind of putting multiple identities in place and multiple ideas and concept in place. Again, not ridiculously hard, just a few steps along the way. So find the exact value, no calculator work here, of sine A minus B. If the sine of A is negative 4/5, the cosine of B is 12/13. A is an angle that terminates in quadrant 3. B is an angle that terminates in quadrant 4. So the first thing I did was read the question. And I said, all right, the question is asking me to find the sine of A minus B. And this entire section is, we're dealing with the sum and difference of sine, cosine, and tangent. So I rewrote this using the identity from the beginning of the worksheet, right? So the first thing I did was rewrite the worksheet identity right at the top, sine of A minus B, there it is. Now I said, I need 4 pieces here. I need the sine of A, which is given to us, beautiful. I need the cosine of B, which is given to us, beautiful. I need the cosine of A, which is, let me see, not given to us at all. Let me think about that. And what about sine B? Not given to us. How am I going to get that? How do we get that? Pause in the video here. How could we get those other values? There are a few ways, but the whole theme of the chapter is identities, right? What other ways, what identities can I use to find these missing values? Have you given it any thought? What identity might come to mind? Yay! If you said the Pythagorean identity, wonderful. If you thought of something else, run with it. See if you get to the same point here, right? So to find these values that I don't yet know, we fall back on the Pythagorean identity. That cosine squared A plus sine squared A equals 1. We were given the sine of A was negative 4/5, so we substitute that value in, square it, do some basic algebra, subtract the 16/25 from both sides, take a square root, and you get plus and minus 3/5. Now, since we're told some more information about angle A, particularly that it terminates in quadrant 3, we know the cosine is negative in quadrant 3. So we don't want to include both values, just the negative 3/5. We make the same argument for sine of B. All right, I'll let you pause this. I'm just going to skip ahead quickly because it's literally the same idea. Substitute in the given information, do your basic algebra, take a square root, read the question. We're told that angle B terminates in quadrant 4. Well, in quadrant 4, the sine is negative as well. So we'll take the value of negative 5/13. Ladies and gentlemen, that's really the most important part of this problem, because if you go back and think about what I've written in black, I applied an identity to the given difference, A minus B. We already had information about sine A. We had the information about cosine B. I had to do some legwork to find cosine A, written in green. I had to find the sine B, which is some type of mustard yellow orange type color. But anyways, we found that value. So now it's a matter of just substituting in those all 4 pieces, all 4 values, doing some arithmetic, and we're done. So with no further ado, Pay attention to your signs. They do get a little bit messy. Work carefully. The product of -4/5 and 12/13 makes -48/65. The product of -3/5 and -5/13 makes 15/65. And combining those values, we get a final answer of -63/65. Please email me with any questions you have. It is now a good time to rub-a-dub-dub your hands a good 20 seconds and hop onto the Math Lab and complete sections 3.3 and 3.4, respectively titled the sum and difference for cosine and the sum and difference of sine and tangent. I put those together in one lesson. Have a nice afternoon. Again, email me with any questions. That went pretty nice.